Assalamualaikum and good day everyone. In this video, we'll be demonstrating the determination and identification of antibiotic residue in food using liquid chromatography, mass spectrometry, LCMS. This analysis was focusing on food, particularly in fruit from different types. The use of antibiotic is initially important as to inhibit the microorganism growth and help to treat and prevent various infections in animals. However, due to the misuse of antibiotic in agriculture and food production activities, antibiotic residues can be present in our food, which exerting harmful effects on the consumer's health. There is concerns on public health because of the residue of antibiotic in food. In 2022, there has been reported that the antibiotic residues in food are likely to accelerate the development of antibiotic resistance in bacteria, cause allergies, and induce other more severe pathologies such as cancer and mutagenic effects. The analysis was done to ensure there is no disease or health issue regarding the antibiotic residue. These antibiotic residues were determined and identified in food, specifically fruit, using liquid chromatography, mass spectrometry, LCMS.
Next is the reason why LCMS is chosen instead of other non-spectroscopy method. The first reason is because LCMS have high sensitivity and low detection limit. LCMS able to detect low concentration of antibiotic residue. Compared to other non-spectroscopy method, they lack of sensitivity, making them less suitable to detect extremely low antibiotic residue level. Next, multi-compound analysis. In complex matrices, multiple antibiotics or metabolites are present. LCMS allows the detection of multiple antibiotics and their metabolites in a single run. Non-spectroscopy method usually are specific to one compound, which may require a separate test for each antibiotic. Next, the robustness to variety food sample. LCMS able to handle food sample in complex matrices like eggs, meats, and fruits and deal with interfering substances that may affect the result. Complex matrices can interfere physically or chemically. Non-spectroscopy methods are less effective in providing accurate measurement for complex matrices as they cannot resolve the interfering substances.
According to the data, the antibiotic aminoglycosides are very polar, which they usually need to be analyzed using either ion pair reagents or with hydrophilic interaction liquid chromatography known as HYLIC. However, ion pair reagent approach does only analyze all of the aminoglycosides except carcinosin. The use of HYLIC provided consistent result for all aminoglycosides including carcinosin, and the column mobile phase was optimized by changing the buffer strength and pH. Hence, the addition of low-level formic acid and buffer assisting with the retention and the peak shape of the aminoglycosides. This figure shown is the extracted ion chromatograms for the first mass spectrometry of antibiotic from oranges spiked at level 2 with the concentration ranging from 100 to 1000 nanogram per gram. The extraction method for aminoglycoside residues in food usually use acidic condition, for example up to 1% formic acid in alcohol. A higher concentration of analytes can be obtained by using a smaller volume of extraction solution, such as 1:1 ratio of extraction sample to sample. Despite that, the ratio of extraction solution to sample by 4:1 generates the highest signal without causing obstacle for the heated electrospray ionization ion source. This successful quantification allows the analysis of these difficult analytes in different fruit products to be done simultaneously. 94% of the curve had R-squared value of equal or more than 0.99. The figure shown here is the extracted ion chromatography for antibiotic residue spike in different fruits. The recovery and reproductivity data for all residues in oranges were acceptable except for streptomycin and carcinosin as at the lowest concentration is below EPA tolerance level. Data for oxytetracycline at the EPA tolerance level, which is 10 nanogram per gram, has achieved the performance criteria. Penicillin G remained in its original form in most citrus fruit during the extraction of fortified fruit. For oxytetracycline at the lowest spiking level, the amount of analyte was overestimated in lemons and grapefruit. The residues of penicillin G in lemons were calculated as relatively low area counts of penicillin S. This method could determine the residues in apples and pears with acceptable recoveries except for the level that lower than the EPA tolerance. The residue of streptomycin and penicillin G in cherries and peaches were also be able to identify using this method. All the tables shown are the data validation for citrus fruit, palm fruits, and stone fruits. The citrus fruits are including orange, clementine, lemon, and grapefruit, while apple and pear for sample of palm fruits, cherry, and peaches for sample of stone fruits. By using variants of the lowest level extracted samples according to the established guideline, the method detection limits were calculated for this method as shown in the table. The lowest spike level was used for this calculation as this is a multi-class method with a wide range of concentration of interest. The performance of this method was quite good considering the differences in target analyte chemistry, a wide range of concentration tested, and the simplicity of sample preparation.
Next is the advantages of LCMS. The first advantages is LCMS have high sensitivity. Sensitivity refers to the ability of LCMS to detect and quantify trace level of compound. A highly sensitive method is ideal for the trace analysis in complex matrices like foods. Next is multi-compound analysis. LCMS able to detect and quantify multiple antibiotic residues simultaneously in a single run. This method gives a detailed overview of the compound besides saving the analysis time. Next is the robustness. LCMS provide a reliable and consistent data under different system conditions, and LCMS remain unaffected by even a small changes. Lastly, the selectivity. LCMS able to differentiate and identify specific analytes from the complex matrices. Selectivity is very important for an accurate quantification in complex sample. The chromatic columns and mobile phase are the key to enhancing the selectivity. Next is the limitation of LCMS. The first one is high cost. LCMS instruments and operational costs are expensive, ranging from 1 to 100,000 ringgit. The maintenance also adds to the ongoing expenses, so it limits the accessibility for a small lab or facilities with a tight budget. Therefore, the instrumentation facilities can be shared with other laboratories to reduce the operational cost. Other than that, preventive maintenance is performed to minimize the repair costs in the future. Next, the matrix effect. Although it can deal with interference, but the ion separation or enhancement by the complex matrices can interfere with the analyte detection, leading to an inaccurate quantification. Therefore, catchers, quick, easy, cheap, effective, rugged, and safe. A sample cleaner method is implemented to reduce the matrix interference. Other than that, optimizing the chromatographic separation can minimize the matrix effects. Next, it is time-consuming. Complex samples require multiple preparation steps like extraction and filtration, so it takes a longer analysis time. Therefore, automated SPE methods are used which allow a streamlined workflow and minimize human error commonly during sample weighing, extraction, filtration, and dilution. Automation improves the accuracy and provide a detailed information in a shorter run times. Lastly, the environmental impact. LCMS relies heavily on organic solvents like methanol, water, and acetonitrile as the mobile phase. So the analytical process releases chemical waste behind. It is costly to ensure a proper disposal of the solvents and residue from contributing to carbon footprint. Therefore, implementing a green chemistry analysis like using a green solvent and solventless or reuse the solvent as an alternative to reduce the environmental effect.
Variation of extraction efficiency was assumed due to the changes in the pH or buffering ability of the different fruit matrices. An internal standard correction was used on the extracted curve in the matrix as the integrated peak areas for these analytes could be variable and matrix dependent. By using simple filtration or with cation exchange solid phase extraction, the aminoglycosides can be further isolated from matrix components. And that's all from us. Thank you.